Well, it can't be loosely based on the homework.
It also can't be that hard, it's only like the last 10 minutes of class.
Right.
2 minutes. The last one took me 20 minutes.
If you went to 240.
Or like, that's fair enough.
Dude, is that calculator state yours?
I'm trying to charge it. My laptop fell asleep last time, so it stopped charging. It only charges when it's awake.
You need to,
I'm just gonna play like ambient music in the background on YouTube.
so you need to show you how to do the queue function real quick.
Yeah, actually.
Go to extract that. I'll do it. Alright. So, go to, menu, we go probably, and then distributions. Go do normal CEDA. And then you put in here up or down,
Have you put in it? Animator.
your symbol.
I haven't used this.
So it's like,
What is it?
U is gonna be your X bar.
Okay. And then this is just.
That's just, yeah. That's your, standard deviation.
How do you do?
And you do directions, right, so. So you put that button on it, and go to. So you put that. Then you put in your lower limit, your upper limit, and then you put the function, or whatever you put it on. Yeah.
Oh, nice.
C squared over two, and then we like.
Oh, I see.
Yeah, you can do
Wait,
derivatives.
you swear on it?
You can do derivatives, but I don't like to do them. No, yeah, that's second derivatives.
That's pretty cool. Yeah. It's actually my goal.
That helps. Your calculator's at,
It's still got a name on it.
you use like a Casio or something.
Yeah, it doesn't do anything. We had to use imaginary numbers in Digitron. Or no, it was electric circuit analysis.
Or, yeah.
When you're doing like VGS and stuff.
What are you taking this summer?
Signals,
Signals?
intro to OS,
Intro to what?
operating systems,
Oh, you're a computer engineer.
and then business ethics.
The ethics class I took was ethics and science. Ethics and science with Dr. Shepherd.
I have the version of his name.
You know, this is a cool room today. It is. My chair is a little cold.
It's been cold.
What's that? My chair is a little cold.
You know, this is supposedly a controlled air conditioning area. I mean, all the rooms. My office will get real hot sometimes, no matter what. And some of the humidity in 238, 239 sometimes is not there. So I don't know what's going on.
It smells like a flea market in here almost.
All right, I gave you a bunch of homework. I wanted to work through some more of the problems. Do you guys have any specific questions you want me to address right now? Anybody? Yeah, I gave you problems out of section 2-5 and 2-6, right? But I didn't cover the Rayleigh distribution yet. And I'm going to cover it today. I figured you could take a look at that. But are there any questions specifically? I want to work through some problems. Did you have one? How about, we didn't do 2-5.1, did we last time or did we? You got your book? Can you take a look? I'm trying to just work through them. I don't want to spend a lot of time on it, but I get all these problems. And, there's,
I think you did most of the 2-5 ones, but we can do it.
we didn't do 5.3, I don't think, did we?
We didn't do, the last one we did was 5.2, and we had trouble finding that.
Two dash five dot, wait, 2-5.2?
Yes.
Yeah, and that's the one I posted about how I made the error. Might as well just finish, let's do that one just to start there. So any error is corrected. Ah. We got a lot of rain this morning, at least around my area. So this is gonna be 2-5.2, and we're gonna do the whole thing. Give me the specifics, anyway.
Point 2.
2-5.2, we're gonna start there, because I messed up.
The mean is 5 and the variance is 16.
Mean is 5, and variance is what?
16.
6, sigma squared is 16, go ahead.
The fourth central limit is A. 5 fourth central limit.
That's the first one? Okay. To do it, we did actually, there's a formula for that, I almost don't want to do this one, but it'd be the expected value of a fourth central moment would be x minus x bar to the fourth power. And I actually wrote the formula for that down, it's down in there. So, tell you what, let me come back to that. What's part B of this?
The fourth moment.
Okay. Fourth moment, so that's just x squared, or x to the fourth, pardon me. We'll come to that part, C.
The third central moment.
All right, we know that's 0, right? Because it's negative. This right here is gonna be 1 times 3, and then since it's the fourth moment, it's 1 times 3, and then it's gonna be times sigma to the fourth, so that's 3 times 16 squared, whatever that is. You can tell me what that is, but I put the answers for this one up there, if you remember. Well, I wish I had 16 squared. 6 times 3. 712? 768 is it? Is that right? If you have a calculator, just check me on that. That's
Strangely enough, in the solution manual, you wrote the wrong average and the wrong variance.
he has, yeah.
Yeah, he had that X bar was 10 and he had that.
I don't know what's going on with that, but this is right though, this is right,
Yeah.
okay. This moment, we'll get back to, that's the long one, the equation I put down, but we can actually get it by, if we take what this, if we go ahead and say what this is, we can break it out and we can see the fourth central, we can get the fourth moment out of expanding this, and I don't want to expand that right now. Part C is
The
third central moment.
moment.
All right, so the third central moment, the expected value of x minus x bar cubed is 0 by definition, and then the third moment, right? Expected value really of x cubed, correct? That's the one I messed up, right?
Yeah.
All right, so if you look at this thing right here, I know that x minus the x bar here is 5, right? If I take this, and I go ahead and, I'm gonna have to cube this thing, so I take that times x minus 5, and that's x squared minus 10x plus 25, this one's gonna be 5. And then I have to take this and I multiply that by x minus 5 again, so then I have x minus 5 cubed would be equal to x cubed minus 10 times x squared plus 25x. And then the minus 5 would be minus 5x squared plus 50 x, and then minus 125 would be the expansion of that. I'm just putting this thing down here so everybody can see what I'm doing. Last time I messed up on the actual math. But it wasn't on this one, it was in the exercise 2-5.2, if you remember. Did you all see what I put down there in the OneNote? All right, now if we want the expected value of this, which is 0, when we take the expected value of this whole thing, you can ignore that. We know it's going to be 0 because it's a Gaussian distribution. So what we wanted to do was get the expected value of x cubed by itself. And if I take everything else to the other side, that's, and let me combine a few things here on the board while I'm doing this. So combining terms, let's see, x cubed stands alone for x squared. I've got minus 15, right? Get rid of that one. And then the next term is 75x, right? Minus 125 equals 0, or no, minus 125. The expected value of this is going to be wait a second, did I just mess this thing up again? No, that's right. So this comes over on this side, then I take the expected value. This becomes positive 15 x squared minus 75x plus 125. Everybody with me on that? And now, this, when you write it out mathematically, this is the expected value, or the integral from minus infinity to infinity of 15x squared times f of x, I'm just going to leave it as f of x dx, minus 75 times the integral from minus infinity to infinity of x times f of x dx. And then it's going to be plus 125 times the integral from minus infinity to infinity of f of x dx, because that's a constant. That's technically what that's going to be, and that will give us the third moment, right? I'm just writing this down to make sure I'm clear and I don't make mistakes. Now, this right here, the integral from minus infinity to infinity, if we ignore the 15 of x squared f of x dx, that is going to be the mean squared value. And what that would mean is that the actual value of this would be equal to sigma squared right here plus x bar squared. You all with me? All right, I'm just coming over here because that's what's stated in the problem. So I'm getting the second moment, right, using this equation. Now take a look at this. So this is going to be 5 squared plus 16. So 25 plus 16 right here. That's 41, isn't it? All right, now I come over here, and that means when I take a look at this first part, you can correct me if I'm wrong on any of this, but, so this is going to be x squared f of x dx. That is the second moment, and that should be 41. 15 times 41. I don't know what the solutions have, but this should be right. Minus. Now this right here, x times f of x integrated, that is the average value. Following? This is x times f of x, so if we integrate it from minus infinity to infinity, we get the expected value or average value. That's x bar, and x bar is 5, so it's minus 75 times 5, and then it's going to be plus 125, and then the integral from minus infinity to infinity of f of x is 1, so that's just 1. Right? So now, what does all this equal? Can you give this to me? I don't know what the answer is in the book off the top of my head. 365. Is that the right answer? Is that in the book? I didn't bring my solutions down. Do you have the solutions?
Solutions manual is still going by the X bar equals 10 and the.
They use that one?
Mhm.
Wow, this is the right, this should be right. What did you say it was?
365.
Okay, that should be the third central moment. Or the third, the value of average value of x cubed. And for this one, this is one of those, I broke it out. Didn't I write that down last time, the equation for this? We have to take this, and then we have to multiply by x minus 5, and multiply the whole thing, and break it out and do the whole thing. But there's an equation in the book, and I wrote it down last time, and I'll show you what page it's on right now. Hold on. That is. It's given in the book. But these things take a little time. Work through.
So 365.
It's page 72 at the bottom. It's the fourth moment. It's 3 sigma to the fourth plus 6 sigma squared x bar squared plus x bar to the fourth. Do you see that?
So 365, that's the third motion.
Yeah. Yeah. The third central moment is 0.
Yes,
Yeah.
that's the third motion.
Yeah, that's right. And the equation I'm talking about is on page 72 for the fourth moment. If you have it in the books, okay? All right. After that, well, for this one, I'll just put it down. We can do it. If you don't mind, give me that little handy. This is going to be equal to 3 times sigma to the fourth plus 6 times sigma squared x bar squared plus x bar to the fourth power. So that's 3 times 16 squared plus 6 times 16 times 25 plus 25 squared.
$3,793 as well.
It's big. Okay. That was, we did 2.5-1? We did that problem in the book?
I'm pretty sure we did the first one, at least.
Just take a look at it in the book, your mind.
What problem was it?
2.5-1, did we do that one?
It's a random voltage.
Yeah, it was
Yeah, I think we did.
the one this question was based on.
It's the Q function.
The Q functions, yeah, okay.
Yeah.
All right. What's the next problem in that sequence? 2-5.3. Okay, I want to do that one. I'm going to come back to a problem too. That we didn't do. It's out of section 4, but it's kind of a problem that's a little more complicated than we make it out. The solutions aren't, they don't do it justice. But I want to work through these. So this is problem 2-5.3. Can you give me the specs on that?
Gaussian random current has a probability of 0.5 of having a value less than or equal to 1.
All right, so they say it's got a value, or I'm sorry, it's got a probability, so the integral from minus infinity to some point of f of x dx, what was the value?
It was 1.
And that's equal to 1/2, right? They said it's got a value, it's got a 50% chance of being equal to or less than 1. That's what it says, right?
Yeah.
All right, well, that automatically gives you the mean. Because that's the point, if you've got a 50% likelihood of being above or below, that is the mean. You follow me on this? It's the average of. So this gives you right away the mean. And I think that's in the solution. The mean value is going to be 1, right? he says, if you read it, you correct me if I'm wrong, it's got a 0.5 chance of being less than or equal to 1, right? That tells you that's the mean. The mean is always going to be the value where it's the 50% mark if something happens. That's what it comes down to. And I might not have said that exactly, but that's it. All right, now, what's the next part?
So, the question also says, it also has a probability of 0.0228 of having a value
Okay,
greater
cool.
than
It's got a probability of x being greater than 5 is 0.0228, right?
Yes.
Okay, here's the deal. Now, this is where these functions are. This is going to be an inverse problem, but we're going to get the standard deviation from here. This is the key thing. Did anybody look at this one? All right, so now, if you think about the q function, I'm going to use q of x, and he's got a tab in his book. That's equal to 1 over, or really it's the, it's the integral from x to infinity of 1 over square root of 2 pi. Sigma's assumed 1 here, because it's normalized, dxt of minus, and it's going to be x squared over the, u squared, pardon me, minus u squared over 2 du. Now, this is the q function, right? And what it says is, this has a value of 0.0028, so I'm put it over here for q, 0.0228. I looked at the tables, and I also used a math tab to get this. I can show this to you, because I brought the calculator, we brought the computer down here. When x is greater than 5, so now what I do is, I have to take q, but I don't put 5 in there. I put 5 minus the average value divided by the standard deviation. Now follow me? Now I'm going to go to that q function, and the argument I'm going to find when I see what this value is and I do the inverse, this is the argument I'm finding here. So what I'm finding is q of, here it's going to be 5 minus the mean, which is 1, which is 4, over the standard deviation. You can look in your books, you can look this up right now, and you'll find out that this argument is q of 2. I did this. There's an inverse way to do it also. If you have the functional form of q, you can do either a solve for this or whatever. So go ahead, you're doing your q tables there?
Q of 2?
You see it where it's q of 2? All right.
0.2275 times 10 to the minus 1. So
Yeah, it's about 0.228. I think that's rounded, by the way, because did he give 0.228? I think so. Right?
that's what it says in the table. I'm not sure about the book.
No, I think it says that in the prop, does it?
Yeah, it does.
Okay, that means 4 over sigma is equal to 2. 4 simply says that sigma is equal to 2. And so now we got sigma equal to 2, sigma squared equal to 4. Now they ask for something, and what's the next part? But this is a good problem, because now you've got to use the invert. You got to,
So we already solved for the mean, the variance.
Standard deviation, yeah.
So that's part A and B out of the way.
Yeah.
So now we're gonna find the probability that the random variable has a value less than or equal to 3.
okay, this is the probability that whatever this random variable is less than or equal to 3. Now hear me on this. The q function is always from some point to infinity, right? So if we take, this is really going to be 1 minus the q function, and they say of 3, so then I put 3 minus x bar, which is 1, over the standard deviation, which is 2, right? Y'all with me on why I did what I did, class? I'm using that q function. You don't have to use that q function, but it's the one I like, and it's in there, so I'm using it. So this is equal to 1 minus q of, and this is going to be 3 minus 1 is 2, 2 over 2 is 1, q of 1. So that's equal to 1 minus, what is q of 1?
0.15.
0.1587.
0.1?
0.1587.
So this is,
0.8413.
I don't have that written down. I got answers. Hold on, let's see if I can access the answer. .8413. All right. And that- All right, so that checks the box on that one. The next problem is,
I think it was 5.5. So you got 5.5,
all right,
at least in the home.
what is 5.4? Just out of curiosity.
Make them follow the function.
No, I don't worry about the histogram right now. That's the histogram.
There you go.
Go ahead.
2-5.5 or 5.4.
2-5.5. Good.
Okay. Common method for detecting a signal in the presence of noise is to establish threshold level, and compare the value of any observation with this threshold. Threshold is decided that the signal is present. Sometimes, of course, noise alone will exceed the threshold, and this is known as false alarm. Usually, it is desired to make the probability of false alarm very small. At the same time, we would like any observation that does contain a signal plus the noise to exceed a threshold with a large probability. This is the probability of detection. It should be as close to 1 as possible. Suppose we have Gaussian noise with 0 mean and a variance of 1.
Hold on. So now we've got f of x, it's got a 0 mean, and it's got a variance, 3 squared equal 1. So it means that, go ahead,
And we set a threshold level of 5 volts.
ET equal 5 volts. Okay.
And part A is find the probability of false alarm.
All right, now, I'm going to just talk you through, because this is radar stuff. It's used all the time in radar. There's Gaussian noise created by the thermal heat in the amplifier and all that stuff that is inevitable. It's gonna, so every signal that comes back to you when you do processing, on that signal, no matter how careful you are, unless you're running cryo temperatures, you're gonna have Gaussian noise superimposed on it. Remember, when we get a signal back from radar, I want to try to give you some perspective on why this is important. You send out a signal, the signal power density falls off as 1/r squared as the signal goes out. That's 1/r squared. Now it hits a target. So the amount of power that's reflected back is going to be the power density at that target, which is proportional 1/r squared times some constant k times the size of the target. It's called a radar cross-section. Now that comes back, it too falls off as 1/r squared. That means you have 1/r to the 4th fall off in your power density from what you sent. It falls off very fast. Very, very little power comes back to you in terms of the ability to catch power from the amount you sent. And the power density can be in the noise level itself. And there's a lot of other things that happen. So after you get that and you amplify it once and twice, every time you amplify the signal, you have to pull off that, after the signal comes back, you have to strip off the high frequency. using either or digitally defined radar methods, or you have to use mixers and get some difference frequencies and take the lower frequencies, but ultimately you have to get what's called the baseband frequency, and then you have to take a look at the actual power level in the baseband frequency and see if it exceeds some thresholds. But they'll usually take the square root of it, so it would be a voltage. I'm just trying to put some perspective in this. This is a very real thing. So now they're saying, what's the probability of a false alarm? What's the probability of that? It's really the area under the curve beyond 5 for this function. Does this make sense to everybody? The f of x here is standard Gaussian. So that means it's going to have a form of 1 over square root of 2 pi sigma exp to the minus, and this is going to be just x squared over 2 sigma squared. All right, that is the density function, and you'd have to integrate that technically. Now, we know, because we've been dealing with these things, what we can really say is this is the probability for the Q function of x. And now, instead of x, we put down x minus x bar over the standard deviation. We're going to find that. So that's Q of x here is 5. So it's going to be 5 over sigma, which is 1, right? So what is Q of 5? It's small. Can you give that to me? I don't know.
0.2807 times 10 to the negative 6.
0.28.
67 times 10 to the negative 6.
Zero point two 6.7?
867
867.
times 10 to the negative 6.
Alright. Why didn't they put 2.8 times 10 minus 7? That doesn't matter. So that's the value, the probability of having a false alarm in one reading. And I say reading because usually with radar, when you first start, you send one pulse and you say the probability of false alarm in that pulse that you just received is this. Okay, that's because this is if nothing is received back, if there's no target, the only thing you have is noise, so that's the probability. Now what's the next part?
If a signal having a value of 8 volts is observed in the presence of this noise, find the probability of detection.
So then, what do you say? They don't give a different density function. They say that there's a signal, a voltage of 8 volts. Can you go ahead?
Observed in the presence of this noise, find the probability of detection.
All right, well, probability of detecting anything, of detecting a voltage or a signal, of detection of signal is equal to 1 minus the probability of not detecting the signal. And that should make sense to you. All right. So if we're taking it says if a signal of 8 volts is present, what's the probability of detecting?
So shouldn't the probability be really high?
Well, then if it is observed, the probability of detecting it, I'm just going to try to show you this. Here's the Gaussian curve, right? Here's 8 volts. The threshold was 5. Now it's 8, right? The probability of a false alarm, right? A false alarm is going to be the area under this curve, right? The probability of there not being a false alarm is going to be 1 minus that, right? So it should be 1 minus, check me on this. So this should be equal to 1 minus Q, and here it's going to be 8 over 1, or 8, and that's extremely small. I don't know if he has it there.
Yeah. Would it be 8 minus 5?
Well, the threshold is 5 volts, right?
Yes.
But what he's, and this is a poorly stated problem. Normally what they do is they say if there is noise present on the signal, then what really happens is this. And you gotta understand, here's what really would happen, it's the probability, the density function for the received signal would be this, f of x received, this would be received, would be equal to 1 over the square root of 2 pi sigma, and then it's gonna be exp, and then, since you got a received signal, it's gonna actually be the received signal's value, v, or whatever it is, which is 8 in this case, plus, just 8, there is no, yeah, it's just gonna be 8 plus x squared over 2 sigma squared. What it does is throw this whole curve up. It centers it at 8 volts. I hope you understand that. It's saying it was an 8-volt signal that this noise is superimposed on. So then, just follow me on this. This is how it should be done. Here's 5 volts. That's the detection threshold. Now here's my 8-volt signal. Now my Gaussian curve looks like this. All right? I hope I said this. Y'all follow? All right. What you just said makes perfect sense now. You're right. So the probability of detecting it is this area, because now all that Gaussian noise gets centered, not at 0, but at 8 volts, because there is an 8-volt signal. They're saying that. So now what's the probability of detecting it? Well, it would be the integral from here to here, right? Yeah. But now the mean value is 8. That becomes the new mean value. So, let me go back here. Now we use our Q function. Whenever you get a signal, if they say there's a signal out there, it's coming back and it has noise, you just take the whole Gaussian curve and move it out to that point. Say that's the 0, that's the mean. It's like that. It's not really like that. There's more to this. Now you got to find that's the threshold. So the probability of detecting would be the area under this curve, and that would be what? Well, now it would be the Q function. Probability of detecting would be equal to really Q here. The mean is now 8. Follow me? The value is 5 that we want to detect above. So it's 5 minus 8, and the standard deviation was 1, wasn't it? All right, over 1. So that's equal to Q of minus 3, right? And what is that value? It's 1 minus Q of 3. How's that? 1 minus Q of 3.
0.00135.
That's Q of 3. 1 minus, say it again.
0.00135.
And can you tell me what that is?
0.99865.
Is that the right answer?
That's what was in the solution there.
0. Go ahead.
9987.
And I didn't say this last time, and I don't know if the book states it this well, but this is sort of the critical thing. Whenever you have Gaussian noise with 0 mean, right? Whenever you get a signal, a received signal in a radar system or anything else, when you assume when there is a true received signal, and you want to know what the spread is, the statistical spread is on the noise, it'll look like this. Now, here's the deal with noise, remember. You don't know the value the noise is going to have at any point in time. The only thing you know is the statistics of it. So even if you get an 8-volt signal back here, if the noise has a value of less than you might say minus 3, greater than minus 3 volts, small chance, then you won't be able to see the target. There's always a chance of a false alarm, always a chance of a detection. Okay, what's next? Is that it?
I think those are 2-5s.
And-
Assigned at least.
And then the next one has to do with Rayleigh distributions. I'm going to go through Rayleigh distribution and actually the Maxwell-Boltzmann distribution and do some problems. I'll tell you one thing about statistical stuff. You don't, first time I had this course, I had a higher level course in statistics, this probability was with Larson Schubert's book, which you probably don't know about, but it was a senior level course that everybody had to take, and a huge amount of complicated probability and stuff and density functions, but they never told you how they developed them or what they were appropriate to be used for. Then in grad school, you learn about all the reasons why it's so important. And in today's industry, when you're creating chips, fabricating chips, VLSI and all that stuff, the biggest thing is overall yield, the amount of devices that are going to actually be produced that are going to work. And that's heavily based on statistics from the processes that they develop. You'll use it. All right. So, let me go through this with Rayleigh, and I'm not even going to bother with the target stuff, but I'll just tell you. So a Rayleigh distribution is something based on the statistics of Gaussian. So if you have an f of x, Gaussian x, you know that that is 1 over the square root of 2 pi, some sigma, that sigma is the Gaussian sigma, times exp of minus x squared over 2 sigma squared. That's a standard Gaussian profile with a 0 mean. No doubt about it. Now, if you take something and you say, now I want to develop something where, say, I have just positive values, and he gives the example of the power dissipated by a resistor. Power is equal, or wattage is equal to R times I squared would be the value of the power. That's strictly positive, can only, the lowest value is 0. Even though the current could be negative, that can only be, the lowest value possible is 0. So, from this, if you have something where, the way he does it is he uses a bullseye approach, but instead of x and y, if you have radius vector r, square root of x squared plus y squared, this type of thing, that can only be strict positive. And he talks about it, bow and arrows being shot in the target and stuff like this. Well then, if you go through and there's ways to do this, but you'll find that the actual density function for this is called the Rayleigh distribution. And it's equal to R over sigma squared. The sigma is this sigma, by the way, remember, it's back from the Gaussian statistics, times exp to the minus R squared over 2 sigma squared. And that's in his book, and that's called the Rayleigh statistics. It's the Rayleigh distribution. Now, a Rayleigh distribution looks like this. It starts at 0 because of R is 0, 0. It goes to relative maximum, and it kind of tapers off like that. And it looks like this, the f of R. You can get it if you talk about having two functions, x and y, that have Gaussian distributions that are identical. Then you get the Rayleigh distribution just by plugging and chugging on that thing. But, and this comes when they talk about, this is later on when you have multivariate distribution functions, how you actually come about getting the distribution for the Rayleigh distribution. But nevertheless, these statistics are useful. And here's the neat thing about this. When I take a look at this, f of R, if I want the probability now of R from 0 less than R, I can use a random variable symbol here, to some value R. The probability that really the random variable is between 0 and R. Well, that's the integral of R over sigma squared times exp to the minus R squared over 2 sigma squared dr from 0 to, oh, I'm going to use R anyway, I shouldn't, but I'll just circle it. I know it shouldn't do that. But this integration isn't a bad one, because if you let u equal to e to the minus R squared over 2 sigma squared, then you get du equal to minus 2R squared times exp to the minus r squared over 2 sigma squared. All right, if that's u, this is du. Do you all agree with that? I'm just showing you, right? I'm going to get rid of the 2's, make it clear. So, if you look here, make that a minus now, you see how this right here is du. It's actually minus the u, right? With me on that, class? Therefore, this integration, that's actually minus du. That integration will give you minus u. So it would be minus exp to the minus r squared over 2 sigma squared, evaluated from 0 to r. Forgive me for using the same notation. The integrand, I'm integrating with r and the limits are, but I think we're engineers and we know why I'm doing it. I could find those things and all that stuff. Now I just flip the limits, make that r, make that 0, make that plus. So this is 1 minus exp to the minus r squared over 2 sigma squared is the probability of r being greater than any value given. And you can see as r gets large, that goes to 1. Y'all with me on this? Now here's the nice, remember how we looked at tables for Q? You don't have tables for that. You just use your calculator. That'll give it to you right there. Follow me? There's no tables needed for this one. Okay. Now, there's 2 other things that happen with this one. You also have to have the mean for the Rayleigh variable. If you have a Rayleigh distribution, what is the mean of R? This is only for Rayleigh distributions. And he's going to do it. I don't know what page this is on, but I've got the thing down here with the currents and stuff. For this one, it's square root of pi over 2 times the actual standard deviation. Now that sigma has to do with this. It's the Gaussian. Maybe I should put sigma x here. It has to do with the Gaussian distribution. The Gaussian distribution standard standard deviation. Follow me? Then, if we talk about r squared. So this is going to be the second moment of that. That's simply 2 times sigma squared. Again, that sigma is sigma of the Gaussian distributions that are associated with this. Because what they do really, you can get that distribution right here, the Rayleigh distribution right here. If you simply take a function, let's say it's f of, but if you say you get a function, we're going to call it g of x is equal to magnitude of x strict positive. This is going to be the statistics that will result. Your new variable will be, the g of x here can only be positive, have positive values, so it would be an r, you could call it r, if you will. You can just say r is equal to magnitude. And these will be the statistics that come from, or the density function. That's what the reason this thing was developed. But again, that x has the Gaussian stuff. So this is a Gaussian, that's from the Gaussian, not the Rayleigh distribution. It also means that if you look at the second central moment where now this is the standard variance of the Rayleigh distribution. That is equal to 2 times sigma squared, where that's the Gaussian distribution. I said that wrong. This is equal to r squared. That's the second moment. It's equal to 2 times the sigma x squared of the actual Gaussian distribution. And then sigma Rayleigh squared is equal to really r squared bar minus x, or minus, r bar squared, so this would be, r bar squared is 2 sigma x squared minus r squared is going to be pi over 2 sigma x, so this is going to be 2 minus pi over 2 times squared sigma x squared, and that comes out to be 0.429 sigma x squared. I'm just putting this down here. Okay, now, with that in mind, I'm not going to do the Maxwell-Boltzmann right now. Can we do 2.61? And then I want to apply some of these things. Most of this, until you see it applied, doesn't really click with you. Can you give that to me? I think I signed this one.
A Gaussian random curve having 0 mean and a variance of 4
Now that's Gaussian.
goes past through a resistance of 3 ohms.
Alright. So they got something here, plus or minus a voltage, creates a current I, and then it comes and there's a resistance of 3 ohms. Go ahead.
A is find the mean value of the power dissipated.
Alright, when I look at this, now this is section 6, and I think 6 is the section on Rayleigh, right? Well, actually,
Density functions related to Gaussian.
yeah, but, he shouldn't have, he's got this down there. He actually has, for this problem, just mention this. If you take a look at this right here, I can say that the power itself is equal to R times I squared, right? That's the function. For specifically, the power is equal to 3 times I squared. Now, if I look at this, if I want the density function, the power density function for P, it would be F of P would be equal to, and here, it's going to be F of I divided by, and then this is going to be the derivative of P with respect to I, which is 2 times R times I. I'm going to stop there for a second. Here's the classic problem that I itself is equal to P over 3 square root of, it could be plus or minus the square root. Y'all with me on this? Now, so that means we're going to have to take, in here for I, we're going to have to take square root of P over 3 positive plus square root of 3 over P negative. Y'all follow me? And because there's 2 possibilities. So when I go here, I take a look at this, and I'm going to say it's F of I of, and now it's going to be negative the square root of P over 3 plus F of I square root of P over 3. Luckily, they're both the same number. Over 2 times R is 3 times I, but instead of I replace it with the square root of 3 over P. Or, I mean, P over square root of 3, pardon me. I'm getting the density functions where I'm trying to get at this. I take a look at this. And that, well, I can take the 3 inside here when he does it, and then this is the same as that mathematically. So the 2's will cancel, so I get F of I of square root of P over 3 over square root of P times 3. And that would be the density function for write down the actual mathematical function,
In the book, in the chapter, there's just a formula for the mean value of power.
yeah, but, did they want the density function in this one or not?
They wanted the mean value.
Well, the mean value for that one, if you look at this, first, if power is equal to I squared times R, then the expected value of power is going to be equal to the expected value of I squared times R. Do you agree with that? All right, well, that's R times the expected value of I squared, right? Well, it says I's Gaussian, right? That's just R, expected value would be the standard deviation, or I mean, the variance squared plus the mean value squared. Y'all agree with that? If that's all he wants, then this isn't bad at all. So resistance is 3, the standard deviation is 4, so 4, is that standard deviation or variance?
Variance.
All right, if that's variance, so it's 4 plus average value is 0, right? So it's just 3 times 4, that's 12. If that's all he wants, the expected value of the power, is that it?
That's what the answer is.
I mean, but is that what they asked for, expected value? What's the next part?
Find the variance of the power dissipated.
All right. So, the next part was trying to use the Rayleigh distribution to explain that.
2-6.3, I've asked for this probability density function.
Yeah. You can actually get a Rayleigh out of this one, but I think it would be a mess. It'd take a little time. So now he wants the expected value. And was it the,
variance of the power dissipated.
all right. So it's the expected value of P minus P bar squared. That's really what it is. Right? So that's the expected value of power is I squared R minus average value, which we found out to be 12, right? Squared. And there's got to be a more clever way of doing this.
There's a formula in the book.
For the fourth,
For
is this
the,
fourth central mode?
for the variance of the power. It just says the variance of power is equal to 2 times R squared times, the sigma to the 4th power.
Here's what this is. This is the fourth central moment, right? So that's going to be 1 times 3 times, and then it's going to be, this is going to be a standard deviation, it's really going to be the standard deviation to the 4th power of the power, right? And that's the mean of the power. One second. What was the formula you had there?
It was, the variance of power equals 2 times the resistance squared times sigma to the 4th, such that I.
Since power is equal to resistance I squared, then he's saying that sigma for power is going to be equal to R times, and this is just going to be, well, that's not quite as easy. that will work if I had the actual, signal for the file. I'm gonna leave that one go. I'm just out of time too. All right, I'll pick this up on Monday and try to move this thing around and get through it. But I wanted to work some problems. I'll give you a quiz now because it's really not Monday, Friday. We got Friday class. See, it feels like Friday, but the second quiz I'll give it. If you could, just, you can use your books for this one. And I said you could. Now, this is pretty straightforward. I'll talk more about the Rayleigh distribution and go about using it. Try to be a little more clear. One thing, just put your names on these things. I had to walk around my 8 o'clock class and point out several people did not have their names on them.